Hi, welcome to the Calculus 3 lecture series. And we're going to start a new unit right now. And this new unit, we call this the vector calculus. And in this new unit, we're going to talk about, the calculus things over the vectors. Okay, so for the first lecture in this unit, because we're going to talk about the vector calculus, so we're going to first introduce what is the vector functions and what is the space curves here, okay? And so let's go ahead and get started. And so here, so vector functions here, if you remember, okay, in the in your either calculus 1, I think in the calculus 1 here, right? And you guys talk about the parametric function. So you can define the x is a function of some t, y is equal to a function of some t's here. And then you can define some type of the curves on the R2s, right? So the one we typically define is like we said, x equal to the like a sine t and y equal to the cosine t's, right? So then we can define that because of a sine t and a cosine t, now we said x squared plus y squared is equal to 1. Then that means we defined what for the t's here, we defined a unit circle, we defined a circles here. That's what we did in the calculus 1. We defined parametric functions here. So in here, we talk about vector function is very similar to the parametric function. You just expanded that to the R3s here. So first things here, we said vector functions, and then sometimes we say is the vector valued functions. Okay, so we use the R to represent vector functions here. And then it's associated with a real number. Okay, so it's a real number t's here. That's our kind of like a parametric function t, right? So we call this vector RT. So the domain of the functions is all the real number t. So the domain of this vector function, so the domain for the RT really is the t's, right? So this is to be, is the real number. Depends on how do you define your functions here. Is it the domain for the t's, right? So it's the real numbers here. So for the 3-dimensional vector, that's why in here we call it vector functions. You can expand it to the 3-dimensional, 4-dimensional, 5 dimensions, right? So for the 3-dimensional vectors, so we have the what? We have I, J, K. So it's X axis, Y axis, and Z axis here. So for each one here, we have what? So we have a real value function, f of t, gt, ht. So those three functions is just the function of the real value t. And then, so we call it the f, g, and h are the components functions here. So like in here, there's several things in the real numbers, like when you talk about in the calculus 1, the function f of x or f of xy. So the same things, be the truth. So if you want to find the limits, right? So if you want to find the limits for the vector functions, and it will just be the same thing. You find like when we say the limit t approach to t0, and then so it's the same thing. You just let what? You just let the, the limit for each component functions. Then you will find the limits for these vector functions here. And then the same definitions, right? When we talk about the real number function, if it's continuous, that's the limit has to be equal to the function value. So it's the same thing applied to the what? The same idea applied to the vector function. So if vector function is continuous, then the limit of the vector function has to be equal to the value of this vector functions here. Okay, so the most important part in here is what is the range of the vector functions? Like in the calculus 1, when you talk about the parametric function. So the range is a curve in R2, right? Okay, so the range of this vector function, okay, so it's a set C of all the vector RT, and the T is in the domain. So those vectors in the RT, in the C, when thought of as point tracer, this is what is most important here, is to trace a space curves here. Okay, so that's why we say the curve C is defined parametrically as the X, Y, and Z here, right? So this is exactly go back to, you know, what we learned in the calculus 1, the parametric function. So now we just in the R3. So instead of the curve in R2, we have a space curves here, right? So, okay, so like in here, that's why, you know, you have the, this is the domain for the t's here from A to B, right? Then each one you generate a what? Each one you generate vectors, right? So then these vectors here, right? See here, you know, when the t from A to B, so this vector, so the vector switch from here to here, right? So it's all the point. So this arc, right? So this is the space curve, right? So you generate by using this parametric relation. So it's on the space. So it's just like the parametric function we defined in the R2, you generate a curve like a while ago we say x equal to the sine theta, y equal to the cosine theta. Then they generate what? They generate circles, right? Okay, so this definition is quite simple here. And so let's take a look at some examples here. So for these examples here, we say, okay, so for this vector functions here, right? I have this is my components functions, right? So my components function is 2t and 1 over t and t plus 1. So we are thinking about what is the domain of the RT. So the domains here, that means is the, we know the domain is the value of what? Is the value of t's here, right? So for the t's here, because this is a domain for the t, and the t is in all these components function. So all these components function has to satisfy. So for 2t, this is my first components function. So what is this one? The t can be what? All the what? Real numbers, right? So that does not have any restriction. So the next components function is negative 1 over t. So for here, what is the t value? We say, hey, t can be anything in the, it's all real number except t is not equal to 0, right? Because the t cannot be in the, 0 cannot be in the denominator. Then the last ones here is the square roots of the t plus 1. So it's the same thing for the square roots. We know the square roots has to be greater than equal to 0. So it's x plus 1 greater than equal to 0. So x is greater than equal to negative 1. Okay, so now when you define the domain of the t's here, it has to satisfy all these three conditions because it has to satisfy all the components functions here. So what is my domains here? Right? So domain is x has to be greater than equal to negative 1, but x cannot be equal to 0. So we say this is my domains, right? It's greater than equal to negative 1, but it cannot be equal to 0. Then you union, and then what here? 0 to infinity, right? So that's why you put a parenthesis on the zeros here because the t cannot be equal to 0. So here. Okay, so now we say, okay, find what is the R2. So it's just like we say, okay, R2, so that means my t value is 2, right? So you will have what? You will have a 4i minus what? You plug the 2 in, so it's 1 over 2j, and the plus the square roots of what? 2 plus 1 is 3, what? Is 3k here, right? So it's 4i minus 1/2 plus square roots of the 3k. So this is the vector in the space. Okay, so the same things here, if you want to find the R1s here, right? So R1, that means you put each component's function with the function value -1. So this is -2i plus 1j. -1 is plus 0 what case here, right? So this is will be my, so it's -2i plus j, okay? So it's just like we're dealing with a real value, like f of x and y. Right now, we're defining this is what we call it is the vector functions, right? So I have like the different components here, all right? All right, so now for the next things here, so they give us the RT is equal to the sine t, t squared plus 4 and the ETs here. Now we want to find the limit, the RT when t approach to 0. Okay, so let's take a look. How do we do this? Okay, so t approach to 0 is just like we did in the calculus 1, you put the limit into the each component's functions here. So this is a limit t approach to 0 sine t. So what is sine 0 is 0, right? And then we said limit t approach to 0. This is a t squared plus 4. So what is here is 0. Then we said limit t approach to 0. This is et. So what is here is 1 here, right? So that's basically, this one's here will be 0. Oh, I'm sorry, this is a 4, right? So this is a 4. 0, 4, 1 here. That will be my limit for this vector function here. Okay, so then the next things here we're going to talk about. All right, so in here, so I'm just want to demonstrate what do I mean a space curve here, right? So in here they say use the 3D to the calcplot 3D. That's the software, and remember I recommend you can use if you want to take a quick look to scratch. To sketch the graph, RT is equal to 1 plus sine ti, 1 plus sine tj plus tk for t greater than 0. So here is what you input, but basically this is the output. That's what we call is the space curves here, right? So when the t change from greater than 0 to the infinity, so this is how the space curve, right? So this is the x-axis, this is y-axis, and this is z. That's how the space curves go. Okay, so let's take a look for the calcplot 3D softwares here. Let me exit here and go to the softwares here, right? So if you launch the calcplot 3Ds here, right? So the graph you choose here, that's why you see a option called space curves, right? So you choose the space curve. And so what do you do here? Then you just type in your functions here, right? So the functions here, we have here is the 1 plus sine t. And then the next one is also is 1 plus sine t. Then the third one here is just t's here, right? And then you can choose the different value here. Let's say t is greater than 0. Let's say less than, you can give it a number less than 20. You want to plot it, right? Okay, so the sine t, okay, so let's say we missed the parentheses here, okay, so the sine t, okay, so here, this is the sine t, oops, sine t, and here, all right, now let's do a graph again, all right, so see here, that's what you get the, that's what it is like, you get the space curve if you let the z, so you can change. So in here, you can change the, the coordinates, so make the curve show more, because right now my z is only at the 2 here, right? So you can change the coordinates and then show the whole graphs here, right? So that's why I did here, right? So I used the software. So that's why you just need to make sure you use the software called the space curves, right? So if you change the z value, so see here, the z, I put the maxima is 16th here, right? So that's why you can see the curve, how it goes, right? So that's what we call this, the space curves here. Okay, so now let's take a look at the next examples here. So let's say, hey, let's take a look, right? So I want to find the functions, right? So I want to find the vector functions here. I want to find the vector function, and whose graph is a line segments from the 1, 2, 1 to 4, 6, 5. Then they say use the 3D to verify it, okay? So how do I find these ones here? So I will say in here, right? So we know for the line in the R3, so from our first unit, we need to can use the parametric forms, right? So the first ones here, we need to have the directional vector, right? So the directional vector will just be from this point to here, right? So basically, so from 1, 2, 1 to 4, 6, 5. So the directional vector will be 4 minus 1, this is 3. 6 minus 2, this is 4. 5 minus 1, this is 4. So here. So this is a 3, 4, 4. That means I know my lines going to the 3, 4, 4 here, right? Then for the parametric form, right? So you remember from the first units, we said the parametric form, you choose a point. So let's choose this point, 1, 2, 1. So the parametric form, I'm going to have 1 plus what? 3t, y is equal to 4 plus 2 plus. Okay, so y is what? Y is 2 plus 4t, and z is equal to 1 plus 4t, right? That's what is the, your parametric function. Then, okay, so now when you go to the calc plot 3t, you choose a space curve. See here, that's how do you input, right? So that's why your input is 1 plus 3t, 2 plus 4t, and 1 plus 4t. So now this is the line segments you see here. That's what we call it, the space curves here. So it's all based on your parametric equations here, right? So it's just an extension about what you learn in the calculus 1 from the R2 to the R3, R4, you can extend that. Okay, so let's take a look at our last problems for this section, talk about the vector functions here. So now the problem number 5, so let's say, hey, do the number, curve RT, t plus 3, t squared, 2t plus 1, and another space curve, 10 minus t, 3t minus 11t, only intersect. Okay, so here we say solve it algebraically and using calcplot 3D. So here I use the calcplot 3D. I input into the calcplot 3D these two space curve. Hey, I do notice they intersect here. Okay, so now how do I solve algebraically? Okay, so if I solve algebraically, that means in here, so that means for any given RT, and so for the other parameter, I cannot use the T as here. So I said S of the K, just give a different parameter to see. So that means if they intersect, these two has to be equals, right? So now you can say this T plus 3 is going to equal to 10 minus K. The same things here, this is T squared is going to equal to the 3K minus what? Minus 11th, right? And then the last component is 2t plus 1 is equal to what? Is equal to k here. Okay, let's try to solve this equation. So from here, I see this is a t plus 3 is equal to the 10 minus. Okay, so I see the k is equal to the 2t plus 1. So I can replace it. So this is a 2t plus 1. Okay, so this is 10 minus 1, so it's 9 minus 2t is equal to the t plus 3. See here, right? Okay, so 9 minus 2t is t plus 3, so it's 3t equal to 6. So t is equal to 2. Okay, so when t equal to 2, then k is equal to the 2t plus 1. So k is equal to 5. So when I change the k equal to 5 and t equal to 2 to my original, so I know, so the R2s will give me what? 5, 4, 5, right? Okay, so the same thing is here. S2, let's see what I have here. So 10 minus k is 5, right? And 3 times 5 minus 11 is 4. And 5 is here. They equal. That's why these two intersect. And they intersect at the point 5, 4, 5, right? That's what the calcplot 3D verify that. All right. Okay, so that's it. This is our first lecture. It's a pretty simple lectures here. We talk about the vector functions, and the most important part in this lecture is that the vector function is kind of the parametric equation. So in R3, they define the space curve here. All right. Okay, that's it. So like a vector function, all the like the function characteristic vector function should have, like for example, how to find how to find the domain, how to find the limit, is this function continuous or not, they have to follow what is a real number function. So our next video, we're going to talk about how do we take the derivative, how do we take integrations, about those vector functions here. Okay, that's it. And like I said, this is a very simple and easy lecture for our first lecture before we introduce the vector calculus, different topics in the vector calculus here. So this is the foundation work we need to know. Okay, that's it. All right, so looking forward to talk to you in the next video. Have a nice day. Bye.